Yes, I just went. Oh, no, I feel bad that I wasn't able to get the right. Yeah, that is great. I'm here in the house. I came for yeah, 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 yeah. 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 Yeah.
Okay, we will introduce from here. Oh, yeah, yeah, okay, that's good. Yes, no. Take it.
Okay, so let us get going. Good afternoon. Welcome to today's colloquium by Professor Heng from School of Chemistry, Chemical Engineering and Biotechnology from NTU, Singapore. Before I even say a few more words on this particular forum, I would like to thank my my counterpart, if I can say that, Professor Jyotishman Dasgupta, the Wednesday Colloquium coordinator, and also Ankona for making this proposal and making this talk possible here. And said sincerely want to thank both of them. Um, for those of you, especially to the speaker who may or may not know what ASSET is for, and also for some of those who are on the social media attending the talk virtually, ASSET stands for Advances in Science, Engineering and Technology. This is one of the three colloquia that happens at TIFR every week. One, of course, where I said Jyotishman himself organizes Wednesday colloquium or Natural Sciences Faculty colloquium that happens on Wednesday. The other one is Maths colloquium that happens on Thursday. And today, of course, every Friday at 4, you have sort of complementary colloquium, on the topics that are more complementary to both Maths Colloquium and NSF. Since one talks about advances in engineering and technology and so on, so the talks are predominantly based on, let us say, detectors, instrumentation, engineering, software, medical technologies, and those kind of aspects. So that is, ASET, of course, is 40-year-old, and this year, incidentally, ASET is celebrating its 40th year of existence, and in some sense, it is very unique. Today, Professor Low is giving this talk on this forum. So without taking more of his time and also all of you, let me now invite Professor Jyotishman to come up on the stage and formally introduce today's speaker.
Thank you, Satya. Thank you for organizing the Asset Forum and always figuring out ways to have people week after week every year. So, thank you. So it's a sort of a sunny day, pretty much at TIFR Mumbai, and inside the institute, things are going on. But my visitor, Professor Heng didn't get a chance to get a feel for it, but he's here inside the auditorium, so I'm very thankful. And I have known him for almost like 15, 16 years. Since I was a postdoc at Berkeley. So just to give a brief introduction. So Heng is an associate professor at the School of Chemistry at Nanyang Technological University, NTU, Singapore. Incidentally, I was also supposed to join him there, but he received his SB from MIT. He did his bachelor's at MIT and worked with Professor Dan Nocera, the closest you can get to Amy Palmer's kind of a work in organic chemistry. And Amy, thank you for coming in. And then he moved for his PhD, pursuing a spectroscopy line, because that's what he found his passion was after his work in Nocera's lab, and moved to University of California, Berkeley, to work with Steve Leone. And Steve has been a fantastic of course, outstanding scientist in attoseconds technology, but also has mentored many Indian students, including some of who are faculty at the TIFR, including Professor M. Krishnamurthy, and also guided students from here. After having a short postdoctoral study at Ferenc Krause's lab, who is the Nobel Prize winner this year, he moved to start his independent career in 2010, and he has been there ever since, looking at a sort of very interesting ultrafast ionization-induced phenomena in gases, liquids, and in aqueous solutions using transient X-ray technologies, and he's been doing some beautiful fundamental work on sort of protonation, deprotonation dynamics in ionized water. And this is something that sort of is telling us fundamentally what are the timescales of proton movement in such systems. Because of his beautiful work, he has been awarded the Nanyang Assistant Professorship, the Asian and Oceanian Photochemistry Association Prize for Young Scientists, and the Chemical Society of Japan Distinguished Lectureship. He's also currently the Associate Dean at the College of Science in NTU. So without further ado, let me welcome Heng Lo, or as Professor Dan Nocera said, Zilo. So, thank you.
Okay, good afternoon, and thank you for coming here on a Friday evening, and thank you to Jyotishman for being such a gracious host and not embarrassing me further. Yeah. Okay, so today I want to tell you about some of the work we've been doing on ultrafast spectroscopy. to capture these transient species in ionized liquid water. But before that, I just want to spend, maybe 1 minute to tell you about some of the other research activities in my group. Okay, so part of my group also works on using these intense laser pulses to study the mechanisms of vibrational wave packet generation in ionized molecules in the gas phase, and probing them using the tabletop XUV sources over here, yeah? And then the other part of the group, actually the part of the group that attracts funding and pays all the bills, is looking at these materials. Yeah, so we use few cycle laser pulses to reconstruct coherent exotonic motion in semiconductor nanocrystals, looking at coherent phonons in nanoplatelets, electronic depolarization phenomena mediated by these Ian-Teller distortions in the nitrogen vacancy defect in diamond, and then looking at some of these ultrafast dynamics in two-dimensional materials. And more recently, we have also assembled a time-resolved photoemission electron microscope to look at the ultrafast dynamics and also to image them with something like couple tenths of nanometer resolution. So the questions that we want to try to address in these types of measurements is, how do the different types of defects in your two-dimensional materials affect their optoelectronic performance? And coming from an ultrafast spectroscopist training, I mean, this is a very rich area to investigate. And on this apparatus, we have also successfully interfaced the time-resolved photoemission microscope to a femtosecond vacuum ultraviolet light source, which allows us to image the dynamics over the entire first Brillouin zone of these two-dimensional materials. Okay, so that's just a brief introduction, but now let's jump into the talk. So when liquid water interacts with high-energy radiation, okay, it can be ionized. I'm sorry, I'm not very good at this laser pointer. I'm better at real lasers, I swear. Okay, so it can be ionized, it can be excited, or an electron can be attached to it. Okay, and then you see with these different phenomena, it generates these highly reactive species like the water radical cation, the hydroxyl radical, the hydrogen atom, the oxygen atom, and so on. And all of these reactive species forms the basis of radiation chemistry and radiation biology. Now, in my group, we have been focusing on the ionization pathway, which is highlighted here in yellow. So despite its fundamental importance, there are actually still a couple of unresolved issues about how ionized liquid water behaves on the ultra short time scale. Okay, and I'll give you a couple of examples in the next few slides. Now, the first thing is that we know when we take neutral liquid water and we ionize it, okay, this electron, it's actually still in water, but it forms this quasi-free state, which the community has called the conduction band electron. I mean, it's not a conduction band in the sense of the periodic systems that we are used to thinking about, but nevertheless, this is just borrowing terminology from the community, okay? And then subsequently, this quasi-free electron, which is delocalized over many water molecules, will find a trap site, okay, a defect essentially in water, okay, into which it will localize and eventually forming the hydrated electron over here, okay? Now the question is whether this relaxation from the so-called conduction band electron to the hydrated electron proceeds via an intermediate electronically excited state, okay? Now earlier measurements saw this absorption in the short wave infrared over here, you can see, and over here as well, with lifetimes of a few hundred femtoseconds, and that was ascribed to the existence of this intermediate state, what they call the P electron, or sometimes the prehydrated electron or the wet electron, okay? But more recent measurements with higher time resolution. So I should point out that these pioneering measurements were actually done on cuvettes with path lengths of maybe like 1 centimeter, using these very intense few hundred femtosecond dye lasers, which have been frequency doubled, okay, to roughly 300 nanometers. So for those of us who do ultrafast spectroscopy, we know that this is a recipe for a lot of coherent artifacts, okay, and also for pulse broadening as well. So more recent measurements for example, done by the group of Steve Bradford at the University of Southern California, with higher time resolution and performed in a liquid jet of a thickness of about 200 microns. They show very nicely that this spectral blue shift is actually due not to the formation of the intermediate state, but rather due to the formation of a vibrationally hot hydrated electron ground state. Okay, so it goes from the conduction band to the S star and then finally to the S, where S star is the vibrationally excited state. Okay, but one thing to pay attention to is that this probe region only spans 500 nanometers to 1000 nanometers. So they're actually looking at the dynamics over a much narrower spectral range compared to the earlier studies which go out, you see, to 1.4 micron or even 1.5 micron. Okay, so there's a little bit of a catch there. And aside from optical palm probe spectroscopy, which is shown by these three panels, these two panels here show the photo emission measurements. So ultrafast photoelectron spectroscopy done on water clusters or even done on a bulk microjet. And there they did not see any evidence of this electronically excited state. Okay, so I think the jury is still out. Now, the second question is, what is the lifetime of the water radical cation? So when you take liquid water, you ionize it, okay, one part gives an electron, and the other part that is left behind is a water radical cation. This is a highly oxidizing species, yeah? And eventually it's known to form the hydroxyl radical. Now the question is, what is the time scale for the formation of this hydroxyl radical? So here we can get guidance from the ab initio MD simulations, where they showed upon ionization, the spin density, so these are the blobs that you see, the spin density is essentially delocalized over the entire simulation cell. Now within 40 femtoseconds, this spin density localizes onto a single water molecule to make your H2O plus radical cation. And then within 400 femtoseconds, this H2O plus radical cation is going to transfer a proton to a neighboring water molecule to give you the hydroxyl radical. So this is the spin density that is left behind that blob. This is the hydroxyl radical. And this thing in green down here, the triangular thing, it's a hydronium species. Okay? And then by averaging their trajectories, many trajectories, they find that there's a lifetime of about 100 femtoseconds for the water radical cation. There have also been experimental attempts to try to observe this water radical cation. So I show you an earlier measurement from the group of Ken Eisenthal, and they ascribe this, I'm sorry, I need to align the laser. This increase, rapid rise, and then the decrease that you can see here, they actually attributed it to the transient formation of the water radical cation. And then the rest of the rise that you see subsequently is the hydrated electron formation. Okay. Now, more recent attempts to observe the spectroscopic signature of the water radical cation predicted by simulations to be at roughly 540 nanometers, however, was inconclusive. So this feature that they see over here was actually attributed to cross-phase modulation artifacts. Okay, so this is the harsh reality. I mean, when you do ultrafast spectroscopy under such high intensities, you are very susceptible to artifacts. Okay? All right. So here's the outline of my talk. So in the first part of my talk, I will tell you about using femtosecond X-ray free electron lasers tuned to the oxygen K edge. So we are doing core level absorption probing to try to understand the ultrafast dynamics of ionized liquid water. Now, the second part, I will switch gears and go from these big accelerator facilities to tabletop facilities. And here we try to understand what are some of the electronic relaxation dynamics of ionized liquid water. And then finally, if time permits, we will talk about some of the ultrafast molecular dynamics, this time in what I call biomolecules, or at least I tell the funding agencies we are looking at biomolecules. You might disagree. And what happens to them when we eject electrons in aqueous solution from these biomolecules. Okay? Okay, so in collaboration with the group of Linda Young at Argonne, Robin Centra at Daisy, and Jan-Erik Rubensen in Uppsala, we went to the Linac coherent light source in Stanford. So this is roughly a 2 kilometer long X-ray free electron facility. It's the first X-ray free electron laser in the world. And we did these experiments to ionize liquid water using intense laser multi-photon ionization. So if, with Ravi's pre-pulse, we can ionize it. We can zap the heck out of this. But this is what we are looking at, okay? And then after ionization, this is the pump pulse. We then send in the XFEL probe pulse, okay, which is tuned to the oxygen KH. So here is a schematic of the experimental setup. So the X-rays come in from here. They are focused by a pair of these KB mirrors onto the target. And then almost in a collinear fashion, we bring the strong field ionization pulse onto the liquid jet as well. So this picture here, maybe you can't see it very clearly. It's kind of dim, but you can see a stream of liquid going down all the way down to the catcher. So this thing is a catcher. So in this schematic, you will see we have 3 different detection channels. Okay, the first detection channel is over here. So we look at the X-ray that is transmitted through the sample. So this requires us to actually use very thin liquid sheets. Okay, so if you try to use like a 3 micron, 4 micron liquid sheet, it will not work. It needs to be 1 or 2 microns. Okay, now this is the first detection channel. The second detection channel, these avalanche photodiodes over here. So we are detecting the spectrally integrated X-ray emission. And the final detection channel, which I will not cover today, is spectrally resolved X-ray emission. So AKA these RIX types of measurements. Okay, so let's look at what the transmitted data looks like. It's shown over here. This is the raw data. So the dashed line, the data below the dashed line is what we call positive time. So that means the ionization pump pulse arrives at a sample before the X-ray probe pulse. Okay, so that means at negative time above the dashed line, there's nothing happening. We are just probing with the XFEL pulse liquid water. It's down here below the dashed line that we are probing ionized liquid water. So this is showing you the transmitted X-ray intensity. And you can see at positive time, there is a depletion. Okay, so the transmission decreases over here. That means there's a new absorption resonance coming in. Okay, now how do we understand the nature of this absorption? We can look at the molecular orbital picture of isolated water molecule. So in neutral water, the HOMO, the 1b1 orbital will be doubly occupied. Okay, so with this intense laser pulse, when we zap water, we will kick off an electron from here into the continuum. Okay, and then what happens with the X-ray probe? Now with the X-ray probe, you have a new transition appearing, right? So for neutral water, the X-ray transition will be from the 1A1, so this is the 1S or the oxygen KH, up to the LUMO over here. Okay, so this transition gives rise to the pre-edge feature that you see in the X-ray absorption spectrum of neutral water. But now for ionized water, you have a new transition. The new transition is from the oxygen K shell to the, what would you call it? The singly occupied molecular orbital. Okay, and this new transition will be downshifted from the original transition essentially by the HOMO-LUMO gap, right? Which in the case of water is 8 eV. Okay, so you expect this new transition to be shifted to the low photon energy site by 8 eV. So this is the pre-edge over here. Okay, and this transition here is indeed downshifted. Okay, so this is how we understand the qualitative features of this data. Now let's take a closer look. Okay, so we consider a sequential process. First, after localization, we make this water radical cation, and then with a certain rate constant, it undergoes proton transfer to form your hydroxyl radical. So this is the first process. Okay, and then in the meantime, the hydrated electron is floating around. Now, eventually what is going to happen is that the hydroxyl radical is going to undergo geminate recombination with the hydrated electron to give you your hydroxide species. Okay, and this is going to happen on a much longer time scale. So now when we do global fitting of the data over here, so this has been converted to X-ray absorption. So this is differential absorption on this color scale as a function of photon energy and time delay. You can see that we can actually fit it to by exponential kinetics. Now the 2 time constants are shown over here, roughly 200 femtoseconds and 14 picoseconds. So when we saw this, we thought, oh, we're very happy because maybe this 200 femtosecond is a lifetime of the H2O+. But before we jump to conclusions, let's take a closer look at a different set of data. Okay, so in this other data set, you only see 3 time traces. Okay, and these 3 time traces are collected at different photon energies. The time trace in gray collected at roughly 526 or 525.93 eV. This corresponds to the absorption resonance of the hydroxyl radical, the end product. Okay, and then in red, this time trace is collected at a photon energy that is slightly detuned to the red. And conversely, for the blue trace, this is collected at a photon energy that is slightly to the higher photon energy side. Okay, now if you look closely at these 3 time traces, you notice that at early times, they don't overlap. There's some offset, yeah, which you can see more closely if you zoom in. Yeah, so we see a delay of roughly 100 femtoseconds. Now, if we do global fitting of these time traces, what we find are these 3 time constants. Okay, so tau 2 and tau 3 are very similar to the previous set of time constants that you saw earlier, right? So in this fitting with the higher signal to noise, we are able to recover this new additional time constant. Now the question is, where is it coming from? Where is it coming from? Okay, so for this, we turn to Robin Santra, our longtime collaborator. Robin can simulate anything and everything. Okay, so I'm not a theorist, but these are the simulation parameters. And here, Robin's student, her name is Caroline Arnold. So Caroline basically looked at a couple of things. The first thing that she was keeping track of is what they call the hole radius. Okay, so what is the extent of the localization of the positive charge? So you can see from here, the hole radius or the radius of gyration really collapses within 20 femtoseconds. Okay, so this is the whole localization that people talk about, which she sees from the simulations. This is shown in a trace in blue. Now the trace in red, and the labels are over here, is the extent of proton transfer. Now, how is she actually quantifying the extent of proton transfer? She is really tracking the distance between the spin density and the charge. Okay, so imagine if you had the water radical cation, the spin density and the charge are spatially overlapped. Yeah, but when a proton starts to move away, the spin density, the hydroxyl radical is left behind, but the proton is moving away. Okay, so this is how she's tracking the extent of proton transfer. And this we find happens on a timescale of roughly 80 femtoseconds. Okay, so the question is the 46 femtosecond component that we see in experiments due to proton transfer? So for that, Robin had to, or Caroline rather, had to calculate the X-ray absorption spectrum. I'm sorry it's not showing up very well, but I hope you can see as a function of pro-photon energy and time delay, there's this bit of a wobble. So it starts roughly here, and then it shifts to lower photon energies, and then comes back out. So in our experiments, we run the time scan out to picosecond or 2 picoseconds, but in Caroline's simulations, she runs it to 100 femtoseconds, because according to her, these simulations take 1 day per femtosecond. And then this was towards the end of her PhD, so you know how it goes, right? So the question is, where is this X-ray absorption feature coming from? Yeah. So here I show you in the red line the line of the spectral shift. So she's plotting how the spectrum is shifting as a function of time delay, and then this other line in blue is the extent of proton transfer that you saw from the previous slide, and you can see they don't correlate. Yeah, the proton transfer coordinate, the proton transfer extent is increasing monotonically. However, the spectral shift wobbles. So they are not correlated, okay? So let's try to look at something else. So what Caroline did was that she then, from her AIMD simulations, extracted the distances between the water radical cation that is undergoing proton transfer and the distance of this radical cation to the neighboring water molecules, right? So there are 4 neighboring water molecules, yeah? And what she sees is this magenta line shown over here. Okay, so the OO distance starts at 2.7 angstroms. This is an equilibrium OO distance in liquid water, and this is known from XF's measurements. And you can see it rapidly contracts within the first few tenths of femtoseconds to about 2.4 angstroms, and then it bounces back to roughly equilibrium. So how do we understand something like this? So remember, upon ionization of water, the charge is initially delocalized, Okay, so in a sense, your water radical cation is not quite formed yet. Yeah, you have some precursors, this is the localized positive charge. And then everything collapses onto a single water molecule. And you can imagine when that happens, the electrostatics, the favorable electrostatics, will draw in these neighboring water molecules with their lone pair closer to it. Yeah? So this contraction of the OO distance that we see at early times, in fact, can be assigned to the whole localization process. Okay, so the positive charge is now localized onto a single water molecule. And then what happens with proton transfer? With proton transfer, now the H plus is leaving behind the hydroxyl radical. The favorable electrostatics is gone. Okay, so the water molecule surrounding the hydroxyl radical will move back to the equilibrium distance. And this is exactly what she sees. Okay, now to make it even more convincing, we look at the dashed black line. The dashed black line tells you the OO distance of all the other water molecules which are not participating in the proton transfer. And you can see they more or less stay at the equilibrium OO distance. Yeah? Okay. So the take-home message here is that when we do X-ray absorption spectroscopy, we are not actually directly probing the extent of proton transfer or the rate of proton transfer, but rather what we are observing is how the surrounding water molecules rearrange in response to this proton transfer event. So, as spectroscopists, it's very important to be clear about what we are observing and how we can correlate it to the phenomena that we try to understand. Yeah? Okay. So anyway, we take this data that Caroline has simulated. Sorry, I don't have the time.
Can I ask a quick question?
Yes, please.
So, have you done these experiments in DT world?
No, we haven't. Yeah, but we would very much like to. But with this XFEL, it's sometimes a toss of a coin. Okay, so but we plan to. Okay, so anyway, we analyze Caroline simulations exactly the same way as we analyze experimental data. We take three lines over here, okay, and then we do global fitting, and we find these time constants. Okay, so 9 femtosecond, which we attribute to whole localization, and then 53 femtoseconds to proton transfer. So based on this joint experiment theory study, we can actually say a few things about the time scale for the ultrafast dynamics in ionized water. And the first thing is water, the positive charge, will localize. So unfortunately, in our experiments, we did not have the time resolution to capture this localization phenomenon. This is something that we hope to go back to the LCLS to resolve. But so we start from here, it's already localized. And then within 50 femtoseconds, the proton goes from this to a neighboring water molecule, making a hydroxyl radical. But if you do the Frank Condon analysis, you will find that actually this hydroxyl radical is going to be in a vibrationally excited state. Okay, and this vibrationally excited state will cool to the vibrational ground state in roughly 200 femtoseconds. And this time scale for the OH cooling process is not so different from the couple hundred femtosecond time scale that is known from, let's say, the nice work of Andrei Tokmakov, where they look at OH relaxation dynamics. Yeah. And then finally, the 14 picosecond dynamics is just geminate recombination. This is nothing interesting. It's been studied to death. Okay. So far I've been telling you about what happens in the near edge, okay, at 526 eV. But if you look at the data, you see at the pre-edge, there's also a shift in the spectrum. Yeah, so where is this coming from? So just to give you a sense of what the X-ray absorption spectrum of water looks like, it's this, okay? So this is the pre-edge over here, okay? And this is the main edge. So the region that we are really tracking is actually just this region over here. So it's kind of like the pre-edge. Okay, the reason why we don't get any information here, you can see there are barely any counts. There are barely any counts because the absorption is too strong. And our jet, unfortunately, was too thick. So this is also something that we hope to resolve. And because now they have these liquid jets that go down easily to a couple hundred nanometers. And you can really go to even the main edge, potentially. But anyway, let's look at what we see over here with this data. Essentially, what we see is that we can take all the time tracers. So all of these time tracers are collected at different photon energies, and these are bin by 0.1 eV. And you can see we can fit them to this expression. So the main point to to pay attention about this expression is that there's only one time constant. So all the dynamics we can explain by one time constant. So from this global fitting, yeah, we get a time constant of about 0.3 picoseconds. Okay, and then we can reconstruct what the differential absorption spectrum, this is the one shown in red, you can just ignore the one in blue, but this is what the differential absorption spectrum in red looks like at long time delays, meaning like 1.5 or 2 picoseconds. Right, so the question is, what is this? So actually, if you look at the hydrated electron literature, you will recognize this time constant here to be the time scale for the formation of the hydrated electron. Okay, so we believe, in fact, that this red spectrum that we see, the red X-ray absorption spectrum that we see, is an X-ray absorption signature of the hydrated electron. And in fact, this is supported by recent nice theoretical simulations done by the Glover group. It's just published not too long ago, where they actually saw, according to their simulations, a blip at roughly 533 electron volts. And you see this agrees very well with our measurements. Okay, so the message here is that X-ray absorption spectroscopy can also look at the electron dynamics. Yeah, but can it look at the dynamics of the excited state electrons? Remember, we have the S electron, the hydrated electron here, but we also were trying to understand whether the relaxation dynamics progresses through the intermediate P electron. Unfortunately, from these measurements, the time resolution was limited, only about 100 femtoseconds. Okay, so to get better time resolution and to have more control over my students, I hope they are not watching this, we did the lab experiments in the lab. Okay, so according to the earlier measurements, this is the well-known hydrated electron absorption spectrum that was discovered by Hart and Borg. And this is absorbing at 720 nanometers. But from the earlier experiments, they also inferred that there is actually this prehydrated electron, or the excited state electron, that is absorbing at roughly 1.2 microns. Okay, so in order to probe this spectral range, we need to generate light in the shortwave infrared. So in the lab, the way we do it is that we take the hollow core fiber output, which is almost octave spanning. You see, it's from roughly 400 nanometers to 900 nanometers. We compress it to about 4 femtoseconds using chirp mirrors, and then we just shoot it into a BBO crystal and drive this intra-pulse difference frequency generation and make this really broadband shortwave infrared pulse, which goes from roughly 1 micron to 1.6 micron, and then we recompress it. Okay, we recompress it to about sub 9 femtoseconds. So at this carrier wavelength, we are talking about, you know, a sub 2 cycle pulse. So the time resolution is good. Okay, so in the experiments, what we do is that we use these shortwave infrared probe pulses to look at ionized liquid water. Now, in the lab, the way we ionize liquid water is that we take, once again, something similar to Ravi's pre-pulse, but this time it's a short pulse, okay, about 6 femtoseconds, and then we shoot it into our liquid microjet. So in these experiments, the liquid microjet is about 7 micrometer thick. So we really want to keep things very thin to minimize any artifacts, to minimize any pulse broadening, to minimize any group velocity mismatch. Okay, so we pay attention to these things, and let's see what happens when we probe in the visible. So voila, this is the visible. So from 600 to 900, so near infrared as well. And you can see this familiar looking blue shift that has been seen by many people, and I'll show you the example from Bradford's nice work. And this is due to the vibrational cooling of the hydrated electron. Now, what happens when we look in the short wave infrared? When we look in the short wave infrared, you can see this very pronounced absorption band showing up, peaked at roughly 1.6 micrometers. Okay. Now, we also did these isotope substitution experiments, which Jyotishman asked about. So in the visible to near infrared, you see the dynamics for H2O and D2O are practically indistinguishable. They are right on top of each other. However, in the shortwave infrared, you can see when we go from H2O, which is the red line, to D2O, which is the blue line, the dynamics slow down. Yeah? So we can do this global fitting of the data and we extract these parameters. But let me try to first explain to you what the model is. So the model is as follows. We start with neutral liquid water, okay? And then we come in with an intense laser pulse to ionize it, and we put electrons into this very delocalized state, the conduction band electron, let's just call it that. And then we have in our fitting, we consider this intermediate state. Lifetime of the conduction band is given by tau CB. The lifetime of the intermediate state is tau P. And then we also account for vibrational cooling of the hydrated electron by this tau solvation. And importantly, we introduce this parameter P direct. So P direct over here is telling me the probability of direct relaxation from the conduction band into the hydrated electron state. Okay, so meaning the probability of relaxation through the intermediate state will be 1 minus P direct. Okay, so let's look at the fit parameters. So these fit parameters are actually extracted from multiple data sets. So we actually took multiple data sets of in the visible to near infrared, multiple data sets in the shortwave infrared. So with these sets of data sets, we can actually mix and match, and we try to make sure that the fitting is really robust. So what we see is this, the lifetime of the conduction band electron. So this should look very familiar because this is exactly what we saw when we probe at the pre-edge of the X-ray absorption spectroscopy. This is also agreement with literature. Now, we also found these lifetimes for the intermediate states, and I'll come back to them in a bit, where you can see a very pronounced isotopic dependence, and this is also suggested by the time traces that I showed you earlier on. And then we see these solvation timescales. Once again, these solvation timescales are known. I mean, they are well characterized, okay? So there's nothing new here. But what is actually interesting is this probability. P direct is 0, okay? And we try to use different various P direct as an initial guess, and every time it would come back to 0. No matter how hard we try, it comes back to 0. What does 0 mean? 0 means that the probability of direct relaxation from the conduction band to the hydrated electron is 0. Okay, that means that all the population that goes from the conduction band has to funnel through this intermediate state up here before it can form the hydrated electron. Okay, all the population has to be pushed through there. Okay, no question about that. But then, what is this intermediate state? What's this intermediate state? So for that, we look at this, these values over here. Now, if you follow the literature on the excited states of the hydrated electron, so if you look at the beautiful experiments done by the groups of, for example, Daniel Mark in Berkeley and Toshi Suzuki in Kyoto, you will see that, firstly, these time constants are remarkably similar to the time constants or to the lifetimes of the p-state electron that they measure in their photoemission experiments. So for example, Dan finds 75 femtoseconds, Toshi Suzuki finds 60 femtoseconds. That's the first thing. The second thing is that the isotopic dependence is also practically the same as what they had observed. So this is actually indicating to us very strongly that the intermediate state is actually the p-state, okay? So then we turn to our longtime collaborator, Oleg Brezdo, to try to understand these experimental results. Okay, so he specializes in running these non-adiabatic ab initio molecular dynamics simulations. And these are the orbital plots that he sees from his simulation. So this is the S electron, and this has that kind of lobe that looks like a P electron. And then these are the population dynamics that he obtains from his simulations, shown in the solid line. So the solid green line is the conduction band population. The solid red line is the p-state lifetime or p-state population, and then the blue line is the hydrated electron ground state population. Now you will also see a set of dashed lines for each color. Now these dashed lines are basically taking our experimentally measured time constants, putting them into our textbook sequential kinetics model, and plotting them out. So there are no adjustable parameters, and you can see the agreement is actually very nice. And here you will see that the p-state population doesn't really build up. Why does it not build up? because the time constant for this is roughly 250 femtoseconds, and the time constant for this is about 60 femtoseconds. So that means the moment the P state is formed, whoosh, is depleted, right? This is your classic, aha, gotcha type of exam question that our kinetics lecturers like to set. So you can see the population really doesn't build up. Okay, so this rise is actually the decay of this, and this decay is actually the lifetime of this. Yeah. Okay. So this was very encouraging, but we also wanted to ask ourselves, what mediates the electronic relaxation processes? Which are the vibrational modes in water that drive these, conduction band to P to S relaxation? So for that, we look at these energy gaps from Oleg's nice simulations. We compute the Fourier transformed spectra, and you can see two spectra over here. Yeah. So in blue, this is the P to S energy gap, and in red, it's a conduction band to P energy gap. Now, in this spectral range, we have three different types of vibrational modes. Okay, we have the intramolecular bending mode, and then we have the intermolecular rotational mode, the hindered rotational mode, or what we call the librational mode. And then at the lowest frequency, we have the hindered translational modes, okay, between water molecules. Now, what do you see about the conduction band to P relaxation? You see that most of the spectral density is actually in the translational mode. So that means for an electron to lose energy to go from the conduction band to the P state, most of the excess energy is dumped into the intermolecular translational modes. Okay. Now, on the other hand, for relaxation from the P state, in addition to contributions from the intermolecular translational modes, you also see significant contributions from the librational mode and the bending modes. Now, why are these two other modes special? It's because when you go from H2O to D2O, these frequencies, the librational mode and the intramolecular bending mode, would rate shift, would downshift by a factor of square root 2. So all the dynamics will slow down. And this explains the isotope effect. Okay, so you will notice for conduction band to P relaxation, we do not see any isotopic dependence, okay, to within the error of measurements. But on the other hand, from the P to S, okay, for D2O, 110 femtoseconds, for H2O, 62 femtoseconds. So pronounced isotopic effects, and roughly factor of square root 2, which is what you would expect. Okay, so we're very happy to see this. Okay, now, before I leave this part of my talk, I just want to address, when we do all these short wave infrared probing experiments, what is the nature of the probe final state that is accessed? Okay, so we know we are probing the P state, and then we come in for a short wave infrared photon, it goes to another state, right? This is the transition that we're absorbing. What is this state up here? Okay, we ask ourselves. So here I show the energy level, I show you the energy level diagram as a function of the solvation coordinate. So at this particular solvent configuration, I'm looking at just neutral water. At this solvent configuration, I'm still looking at neutral water, but with a cavity. The cavity is where the hydrated electron resides. Okay, so the solvent coordinates, they are different. And these values are extracted from the literature. And from our shortwave infrared probing experiments, we can infer what is the transition energy, okay, 0.75 electron volts. So if you put all the numbers together, you find that there's actually this state. Okay, so this is the P state. And from here to up, the transition absorbs at 0.75 eV to some probe final state. But this probe final state is actually a bound state. It still lies below the conduction band. What is this state? Yeah. So then we looked to the literature and we found this nice result by Alfredo Pasquarello, which was published in 2019. And he found this, what he called a wet electron, which was localized or positioned energetically 0.3 eV below the conduction band. So when we first saw this, we thought, we are very happy. Look at the abstract, 0.3 eV matches exactly what we measure. But then read the paper. So when we read the paper carefully, we realized that this solvent configuration is actually not this configuration, but this configuration. So really, it's not comparable. But in any case, we see this excited state, which is located less than 1 eV, below the conduction band minimum. And this motivated us to do these mid-infrared probing experiments. Okay, so go from shortwave infrared now to mid-infrared. Now, many of us will know that it's very difficult to do mid-infrared spectroscopy looking at the OH stretch of water. It's very strongly absorbing. But here we got away with this. Why? Because our microjet is very thin. So in these measurements, we're using like a 1 micron thick jet. And at 1 micron, if you calculate the transmission, it's about 30%. So it's very good for doing transient absorption spectroscopy. Okay. And then the other thing is that you notice, so we did both H2O, this is the OH stretch, this is D2O looking at the OD stretch, and there's this buildup of this new band. And this buildup is happens on this time scales. So this is the third time you're seeing this now. It should get a bit boring. So this is basically the lifetime of the conduction band. Okay, so we believe that this signature that we see, this new absorption band that we see over here and over here, is due to the infrared absorption signature of the hydrated electron. Okay, and there is some experimental support from the resonance Raman experiment. So this was done by Jyotishman's postdoctoral supervisor, Rich Matthews. And sure enough, here they see this OH stretch at roughly 3,200 wave numbers, and this OD stretch at roughly 2,400 wave numbers, which agree nicely with what we see over here. And these stretching frequencies are actually downshifted from the neutral OH or OD stretches by a couple hundred of wave numbers. And the way to understand this spectral rate shift is to remember that when you have this hydrated electron, so this is kind of like the cavern geometry, when you have this hydrated electron and all your OH bonds are pointing into that blob, what happens is that you have some delocalization of the electron density into the OH anti-bonding orbital, which is a LUMO of the H2O. And this delocalization of electrons into the anti-bonding orbital weakens the OH bond and therefore downshifts the frequency. Okay, so this explains for the rate shift of roughly a couple hundred wave numbers. Yeah, but anyway, we then tune to even longer wavelengths. So this is roughly 8.5 microns. And we see uniformly across the entire spectral region a very fast, rapidly decaying dynamics. And the question is, where is this coming from? And then we took some reference from the literature, earlier measurements done by a group of Alfred Lobrow in Munich. They also saw some absorption signature in the mid-infrared, which they ascribed to a complex between a hydroxyl radical and a hydrated electron. But there's a caveat. The caveat is that these measurements were done under different irradiation conditions. So here it was 2-photon UV ionization, which we know today is below the direct ionization gap. So there was some indirect ionization going on, which means there's quite a bit of solvent reorganization that accompanies the formation of this hydrated electron. That's the first thing. The second thing is that the time resolution in these experiments was roughly 300 femtoseconds. Okay, here in our experiments, it's about 60 femtoseconds. So we believe we can see more stuff. Now, if we look at the more recent terahertz spectroscopy measurements, combined with ab initio simulations, they have found that there's actually an inverse relation between the transition energy of this quasi-free electron and the size of the quasi-free electron. So as the size increases, the transition energy kind of decreases. Kind of following like this is almost like a textbook particle in a box model, as they found. So the take-home message is that in the long wavelength region, it seems that the spectral response of ionized water is not so much dominated by the, let's say, OH stretch and so on, but rather it's the electronic response. It's electronic response, okay? And that's our working hypothesis. I mean, this is very preliminary results. We are still trying to analyze it, but the working hypothesis is that we are looking at some other transient intermediate that is absorbing in this long wavelength range. Okay, now time is running out. Jyotishman has a flight to catch, so I will speed through. But if you have questions, please email me and let me know, because I need to hitch a ride from him also, so we will leave very quickly. So the question is, how do we extend these measurements to biomolecules? Because, in Singapore, when you tell people I study liquid water, it's not very exciting to funding agency. They want to see real action. So real action means biomolecules, or to us, biomolecules. Okay, so the question is, how do these biomolecules undergo structural rearrangement after we eject electrons from them? Okay, so if we start from a neutral biomolecule, we eject electron, this is called photoionization. And if we start from an anion precursor and we eject electron, this is called photodetachment. Okay, so that's why you can see photoionization/detachment. Yeah. Okay, so now if you look at the gas phase measurement, so once again, measurements by Daniel Mark, this is now phenoxide in the gas phase. And if you want to study how does a phenoxide anion rearrange after it forms a phenoxy radical, right? In physical chemistry class, we analyze a Frank-Condon progression. From the Frank-Condon progression, we get the vibrational spacing and therefore the vibrational mode. But then, if you look at the photodetachment spectrum of the phenoxide molecule in solution, there is no Frank-Condon progression, just these broad blobs. Okay, so the frequency domain analysis is not going to work out. So what do we do? Well, if you can't do it in the frequency domain, do it in a time domain. Okay, so because of the interest of time, I will not justify why we use phenoxide, but it was a good first choice, and we could tell the funding agency structural mimic for tyrosine, and they were very happy to hear that. Okay, so anyway, yeah, please forgive me, Amy. Yeah, okay, so now we look at the probe wavelength as a function of time delay, and if you look at the absorption spectrum of the phenoxy radical, it's known to have a strong absorption at 400 nanometers. So this is exactly where we're probing. And I don't know if you can see it, but there are these modulations as a function of time delay, these wiggles that you see. So these are vibrational wave packets, okay? And if we Fourier transform them, you can see we get a whole forest of frequencies, which my very talented ex-postdoc, Tushar Debnath, he was a lead author on this. He was very particular about assigning every single blip. And I say, Tushar, please just look at the signal to noise and the statistics. Yeah, before we read too much. And he took the advice. Yeah. Anyway, we were able to reproducibly, robustly assign at least 10 vibrational modes. Okay. And what are these 10 vibrational modes? They are all listed over here. And you can see what we observe and what is calculated is actually in very good agreement. Now, the question is, why do we see these vibrational modes? So here I want to try to explain in this potential energy diagram. Okay, so we take phenoxide along some vibrational coordinate. It looks like a nice harmonic oscillator. We come in and we eject this electron. Okay, so we go from phenoxide, the anion, to phenoxyl, the neutral species. Okay, so this is a vertical process, the vertical detachment process. Okay, so the nuclei does not even know that it has lost electron. Okay, but then up here, you can see the equilibrium geometry of this and this. They are now displaced. Okay, and when they're displaced, and if you strip off this electron fast enough, impulsively, many of you will know that we make this vibrational wave packet motion. Okay, so what this means is that if you see vibrational wave packet, then most likely the two potentials are displaced. And how are the two potentials displaced? The two potentials are displaced because it undergoes structural reorganization. And this is exactly what we're after. So this is kind of the time domain strategy that we have chosen to adopt. So you can see so many vibrational modes. I mean, there's a zoo of them. And interestingly, if you compare to the gas phase photodetachment spectrum, this is the spectrum I showed earlier. If you do the Frank-Condon analysis, you only find one mode, 519 wave numbers, which coincidentally is the strongest mode that we see in the solution phase spectrum. But in solution, you see there are so many other modes that are coupled to this detachment. Yeah, and we try to rationalize that by doing some very simplistic and naive DFT calculations. We looked at the extent of structural reorganization when we go from this isolated phenoxyl species to this microhydrated phenoxyl species. And we find that in this microhydrated species, you can see these structural reorganization extents are always larger than what we see over here. So because of the solvent environment, it really encourages or drives a larger extent of structural reorganization. And perhaps that explains why we see many more vibrational modes, which you would not see in a gas phase experiment. Okay, so we took this strategy and then we went to now real amino acid. Yeah. So You can see all these vibrational modes, and they all look like this, doing their gymnastics, like my 8-year-old son. And then you see most of them actually are localized on the aromatic ring. Why? Why is that? Because if you look at the HOMO, which is in the Koopman's theory, where you eject the electron, most of it is localized on the aromatic ring. So if you eject the electron from aromatic ring, you would intuitively expect a larger extent of structural reorganization around the aromatic ring, which is exactly what we see. Okay, so we took this, we went to tryptophan. Because of interest of time, I will not go into details. We see also very low frequency modes, which we can assign to these intermolecular modes. So when we take the indole ring, we remove the electron, suddenly this water molecule zooms in and drives these structural reorganizations at very low frequencies. We have done it for phenylalanine as well, okay? And then just very quickly, I also want to tell you how we can use this to study chemical dynamics, not just structural rearrangement, but where actually the proton leaves, just like in ionized liquid water. So here we take phenol, okay? And it is known that when you make the phenol radical cation, it's going to lose a proton very quickly. How quickly? So from our time domain analysis, we found actually it's within 200 femtoseconds. Okay, so here the way we do it, I will just tell you in a nutshell. The way we do it is that we track the appearance of the OH WAG and the OH bending mode and how quickly they disappear from our time domain data, right? So we can see all these very nice frequencies, we can assign them, and we can also assign one of them to the OH WAG and the other one to the OH band, and then we see as a function of time how they disappear. Okay. All right. So we have also done in collaboration with real theoreticians at the Wuhan Institute for Physics and Mathematics, these wave packet trajectory calculations, which basically supports the observed lifetime of roughly 0.2 picoseconds. Okay. All right. So I just want to conclude. I see Jyotishman has gotten up. It's time to stop. Okay, so in this talk, I have shown you different ways to look at the dynamics of ionized liquid water. Okay, we can probe in the X-ray, looking at proton transfer and also the hydrated electron formation, or on the tabletop setup with more control over the pulse duration and the time resolution, we can see that actually the relaxation really goes through the intermediate P state. I think there's quite strong evidence for that now. And then in the case of biomolecules, we can actually use this time domain method to try to tease out, how does the biomolecule undergo rearrangement, okay, upon this electron loss. And why is this important, you might wonder? Because you see, it's important for the biomolecule to dump its energy as fast as it can so that it's less reactive, it's less oxidizing. Okay, so it's important to track these things. So none of these adventures would have been possible without very talented students. So Pei Jiang really led the shortwave infrared work. Shafiq and Tusha worked on the ionized biomolecules. Oleg, a very valuable long-time collaborator, Linda as well at the XFEL experiments with Jan Erik Rubensen, Robin Centra, and the wave packet trajectory calculations done in the last part was done actually by a collaborator in Wuhan. Yeah, so thanking the funding agencies for their support. Yeah, thank you very much for your attention.
Thank you.
Yeah, thank you.
This was a fantastic, energetic talk.
Thank you.
We'll take some questions.
Yeah.
Yeah, so very, very interesting talk. So in the initial part, so after you excite the electron to the conduction band, right? What is its role in mediating the proton transfer? Because you have this extra negative charge sitting there, right?
Yes.
It must be impacting the barriers somehow, right?
Yes. Yeah. This is the $64 million question. So actually, in our simulations, to be honest, let's say in Robin Centra simulations, when he is looking at the proton transfer dynamics, right? He is really, you will know this. He is smearing out the electron over the entire box. Okay, likewise, when Oleg Presto is simulating the electron dynamics, he smears a positive charge over the simulation box, okay, to have this electro neutrality. Now, I think what you're alluding to is that there is simultaneous electron dynamics and proton dynamics. They are actually coupled. They should be coupled. Okay, the Coulombic coupling between them should be very strong. To be honest, I tried to convince a long time ago, maybe 10 years ago by now, Mikko Perinello. We spent a long time talking about these things, and it's really complicated. That's one thing. But the other thing is, to me, experimentally, I haven't quite found a good way to see how they talk to each other. Maybe if one can do these, the recent types of electronic vibrational types of 2D spectroscopies that Graham Fleming has pioneered, one might be able to get some insight into this. Yeah, but I have not looked into that.
I'm thinking even if there was no correlated dynamics, but if it was a static electron sitting there, do you think it would still influence the rates?
Okay, so the thing about the conduction band lifetime is about 250 or 300 femtoseconds. This is actually significantly longer than the proton transfer time. I mean, I wouldn't say, I don't know, it's a factor of 6 significant to you. It's a factor of 6, okay? So to some extent, maybe the coupling is not that strong. Yeah, I don't know if that answers the question, but it's something that always makes me lose sleep at night. Yeah.
Thanks.
Yeah, hi. It's a very nice talk.
Thank
So
you.
I was just wondering, like solvent electron spectrum are affected by temperatures. How are these lifetimes affected by temperature?
I beg your pardon?
Temperature.
The temperature depends.
For the
Temperature
lifetimes.
dependence.
For the lifetimes.
Okay. This has actually been measured, and people have also measured the pressure dependence of these lifetimes. But I'm sorry, off the top of my head, I cannot remember the details. But if you drop me an email, I will send you the references. In our measurements, we have not looked at the temperature dependence.
Okay.
Yeah.
Thank you.
Can I ask a question?
course.
A quick question. Oh, you want?
After you. You know, you began with water and
Yes.
trying to, but then you're going all the way to biomolecules.
Yes.
So what you learned from your studies on water, how do you pull that to a large biomolecule with lots of things happening?
Yeah, actually, they are quite separate, I would say, because the biomolecule is more of a solute. And
Exactly.
the water, yeah, so they are separate because, the biomolecule, we don't have this notion of the conduction band and so on. It's really localized. But maybe if you want to say, is there a general theme unifying this, I would say, yeah, perhaps, if you're a radiation chemist, I mean, this would be related to that.
Okay.
Yeah,
So what
but
you learn can be somewhat extended.
not really
bio-
transferable from liquid water to biomolecule. Yeah, unfortunately.
I just wanted to have this discussion on, maybe we can have a later talk
Yeah,
about it,
in the
but
car.
just for audience here, can I project it back to what Sharon does for her PCET ideas, where you have a well-defined donor and acceptor, right? For the
Yes.
proton and the electron.
Yes.
So this is internal now. You have an electron going to the cluster again, just sitting right next to the proton transfer partner.
Yes.
So can you project it back to these kinds of pictures, or it is too strongly coupled where you maybe do not have the Marcus-like picture?
Yeah, this is also $64 million question.
Yeah.
So when you look at the water radical cation, right? So far, what I have presented is just the proton transfer. But
Right.
in reality, the water radical cation is also very oxidizing. Okay, so in principle, if the water radical cation is beside another water molecule, you could have an electron going from one to the other. So basically, the radical cation would kind of hop along.
Right. So now, that's the question is, how delocalized is this, and the temporal dynamics of those hopping of electrons or protons in this case?
Yeah.
Protons will be slower, but
Yeah.
how delocalized are these states? How do they look in terms
Okay.
of
So
initial preparation?
for water radical cation and water, That has not been simulated.
Okay.
However, there have been pulse radiolysis studies where they look at, for example, water and sulfate.
Right.
Okay, so they make the water radical cation.
Right.
And they do all these kinetics measurements to infer how fast does a sulfate anion radical produce, how fast are they produced.
Right.
And they infer actually it's actually competitive. So it's not something that we should ignore.
Okay.
Yeah.
Are there any further questions for Heng? Or we can have one more question. Yes, a student question. Yeah.
Okay. Thank you for the talk.
Thank you. You're welcome.
And this is not a science question.
Oh.
How long did it took you to do all the DFT calculations and define all the vibrations?
Sorry, I beg your pardon.
Science question.
How long did
I'm
I
sorry.
take to?
That's a science question.
And assign all the vibrations to the particular frequency.
Ah, I'm not the one doing it. I just tell the student do it. Sorry, but these are not difficult calculations though. I mean, we have done some calculations where we look at, for example, we try to microhydrate and we see what, how many water molecules do we need to get some consistent behavior. I mean, there have been systematic calculations. I mean, if you look at the supporting info of some of these papers, you will find it there. But these are not difficult calculations. Yeah.
Proton was still localized, even though it's removed. I got an impression from the first part.
Yes.
The proton was still, it was taken out, but still localized in some.
In the hydronium species. Yes.
Not going far.
Yes. Yeah. So, okay, this is maybe still very preliminary, but from some of our infrared measurements, we believe that we see some evidence of the hydroxyl radical proton, what do you call it? The hydronium complex. Yeah, there is some infrared signature for that, and we think we see, but think only. Yeah, need to look closely and do more experiments. Important. Yeah, more experiments. Yeah.
Just nothing else.
Okay.
Okay, it looks really very interesting lecture, and I see a lot of discussion which brought out also many nice insights of your lecture. As I mentioned, Prislo, this is a part of the 40th year celebrations of ASET, and we do have a very special memento that we want to hand out to you. And I request Professor GRK to come on to the stage to do the honors.
So to remember us by.
Oh, thank you so much. Such an honor. Thank you very much.
And we hope to have him back at TIFR.
Yes.
Under normal conditions.
Under normal conditions. Thank you so much. Yeah. Thank you.
Yeah. And I just put it in.
Oh, thank you.
Thank you.
Thank you so much.
Oh, okay. I'm sorry, I forgot to announce. So the tea is being served at the
Cafeteria.
HBA cafeteria.
You can take one more.
Yeah. So